Well, today we're going to work with a couple of basic concepts to start out College Technical Math 1A, and those are the concepts of accuracy, precision, and we're going to move on to significant digits. This lesson will be largely a review of some basic mathematical concepts you've had before, but the topics of significant digits and the difference between accuracy and precision might be new. We have a couple of objectives here. The primary goal is to become familiar with various number systems. We won't work with all the number systems, but a few basic ones. We're going to review some mathematical symbols associated with number systems. That should be largely a review for most of you. And we want to become familiar with the concept of significant digits. We also want to recognize the difference between the accuracy and the precision of a number value. Let's start with number systems. First of all, the integers. The integers are the set of whole numbers, including both positive and negative numbers, including 0. Now, many of you, the first numbers you learned were the natural numbers. The natural numbers are the counting numbers, 1, 2, 3, 4, and so on. Well, after tacking 0 onto the beginning of that and considering all the negative natural numbers, we have what you've got on your screen here, the integer numbers. Now, we can expand the number system by including fractions in this, and all fractions are called the rational numbers. Rational numbers are the set of numbers that can be expressed as fractions having integer numerator and denominators. So we've got a couple of examples of rational numbers on our screen here. 3/4, 9/8, 2 1/3, 88/15. These are all examples of the rational numbers. Now there are certain numbers that cannot be described as fractions. Those numbers are not rational numbers. A few examples of numbers that are not rational. You might think of a few. Pi. Pi is an example of a number that cannot be expressed as a fraction. Another example of a number that cannot be expressed as a fraction. Many roots cannot be expressed as fractions. The square root of 5, for example, cannot be expressed as a fractional number. And another example is another constant, e. E is a constant value. Decimal goes on forever but never repeats. And that makes it a number that is not rational. We call numbers like this the irrational numbers. They cannot be expressed using whole numbers within a fraction in the numerator and the denominator. Well, if we take all the rational numbers and all the irrational numbers together, they form one big happy number family called the real numbers. Within the rational numbers, of course, we worked with one subset called the integers. The real numbers compose all the numbers that we'll be working with in this course. But again, we're going to focus on only the real numbers, that is, the rational and the irrational numbers in this course. Now, a very basic review of some mathematical symbols that you have undoubtedly seen before. First of all, the equality symbol. A equals B means that A and B are, in fact, equal. Equal sign with a slash through it means that A and B cannot and are not be equal. They are not equal and cannot be equal. And a symbol that you've probably seen before, a little squiggly equal sign, means that two numbers are very nearly equal. And that's a relative term, but it means that the two numbers are very close in value, and we can approximate one as the other. The inequality symbols. First of all, the greater than symbol. A is greater than B means that the number on the left is larger than the number on the right. For example, negative 12 is larger than negative 15, and 8 is larger or greater than 5. Many people learn inequality symbols by thinking of the alligator's mouth, and it is always true that the inequality sign, like an alligator's mouth, would always open towards the larger value. It's an old trick, and it's pretty effective. The less than symbol, A is less than B, has the inequality opening to the right, and that means that the value on the right is larger or greater than the value on the left. So, as we can see here, 4 is larger than 3, or we would say that 3 is less than 4, and that negative 10 is less than negative 2. The absolute value symbol. The absolute value of a number is the difference between that number and 0. Now, you've probably seen the absolute value sign somewhere in your studies of math. The symbol for absolute value for a number are 2 vertical bars on either side of the number. Absolute values are always positive, or they could be 0. For example, absolute value of 8. The distance from 8 to 0 on the number line is, of course, 8. The absolute value of negative 3.5 is certainly 3.5. And the absolute value of 9 minus 13 is the same as the absolute value of, if we do this computation, 9 minus 13 is negative 4. And the absolute value of negative 4 is 4. Absolute value plays a role in certain functions, and we'll look at that some more when we do some graphing of functions a little bit later in this course. Now we're going to move on to the topic of significant digits. This is a very important topic, especially for physics and chemistry. To start out our discussion on significant digits, we'll consider an example. As it turns out, not all numbers in a numeric value, not all digits in a numeric value need to be considered significant. For example, let's consider a town with a population of 15,000 people. Now, if I were to tell you that there was a certain town with 15,000 people in it, would you assume that there was really exactly 15,000, or would you assume that I had rounded that off and that the population was near 15,000, probably not exact? You would probably assume that that 15,000 was an approximation. But still, you'd assume it might be 14,000 or a little bit over 15,000 as opposed to, say, 60,000. So for some reason in our mind, we see the 1 and the 5, and we take that more seriously than these zeros. You'd believe that it's about that the 1 and 5 are approximately true, but you don't necessarily assume that these zeros are correct. And that's a natural assumption. These zeros would be said to be insignificant. They would not be considered significant digits. Whereas if I told you that a town had a population of 14,893, you would assume that that really was the population. You would assume that this was not a rounded off value, but in fact exact. You might say that you're taking all of these digits very seriously. You assume that they are all correct, whereas these last 3 zeros you assume to be approximation. Well, if we look at these two numbers, we count the number of significant digits in each number. Here, the 1 and the 5 are significant, but these 3 zeros are not. This number would have 2 significant digits, or sigdigs. This number, however, all 5 of them would be considered significant. So what exactly determines whether a number is significant? Well, first of all digits 1 through 9 are significant. And some zeros are, but not all. So that's why this number automatically has 5 significant digits. All the digits 1 through 9 are automatically significant. But if we identify zeros that are not significant, these type right here, that are only there to approximate a value, they are zeros that are only used to locate the decimal point. For example, if that 0 wasn't there, this number would become 1500 or 150 if we lost 2 of the zeros. So those zeros need to be there in order to put the 1 and the 5 in the right spot. That means these zeros, the only thing they're doing really is locating the decimal point, showing that it's 15,000 instead of, say, 1,500 if the decimal point were to float back here. Since these zeros don't actually represent the exact population, all they're doing is holding the decimal point in the right spot, they are considered insignificant. The 1 and the 5 are significant. Those are our 2 sigdigs, but these are not. Let's consider some examples. We're going to look at a few different numbers and determine how many significant digits there are in each of these number values. The first example we'll look at is 5,070. 5,070. Anytime we have a 0 that's between 2 non-zero digits, that 0 is significant. It's not rounded. We wouldn't round it off here but then unround at 70. And so this 0 certainly is significant. Anytime a 0 is between a non-zero digit, it is automatically significant. This 0, however, could be rounded off. This could be rounded off to 70. It might be 5,069. It might be 5,072. Since this 0 is hanging off the end of the number and its only job is to locate the decimal point here, we would assume that this 0 is not significant. This one is, and so we have 3 significant digits. Another example. 500. These zeros are only here to push the decimal point out and put the 5 in the hundreds place. 5 is our only significant 0 here. These 2 are not significant, and so this number has 1 sigdig. Let's look at some numbers containing decimal points. 4.70. Notice here that the 4 and 7 are automatically significant. But ask yourself, is this 0 showing additional precision or additional ability of whatever tool measured this value? Or is this 0 only used to locate the decimal point? Well, it's doing more than locating the decimal point. In fact, it's not locating the decimal point at all. That 0 plays no role in where the decimal point is. Therefore, it is significant. Since this 0 is significant, along with the 4 and the 7, this number has 3 sigdigs. That 0 shows additional precision, which is one of the next topics we're going to work with. If we were to compare that number to, say, 4.7, this number only has 2 sigdigs. For example, if we measured the height of a desk and it was 4.7 feet tall, we might measure it even more specifically to see that it's 4.70 feet tall. This would be measured with a more accurate tool than this one, and therefore the 0 does carry a meaning other than simply holding the decimal point. Again, the key is to look at that 0. Is it used to locate the decimal point, If it's not, it must be significant. It must have some other role. Let's do a few more examples. How about 0.5? This number is the same whether that 0 is there or not. 0.5 is the same as 0.5. That 0 carries no additional meaning. It is not significant. The 5 is the only significant digit here. .0072. How many sig digs do we have here? We have 2. These zeros are only used to locate the decimal point. The 7 and the 2 are the only significant digits. If those zeros weren't there, it would change the value of the number to .072 or .72. So those zeros are there to push the decimal point out. That's their only job. Therefore, they're not significant. And so here we have 2 sig digs. .05170. How many significant digits do we have here? You'd all agree that the 5, the 1, and the 7 are significant, so there's 3. Is this 0 significant? It is. It has no role in locating the decimal point, therefore it shows additional precision. It measures out to the 5th decimal place instead of the 4th, so this one is significant. This 0 is not significant. It's only pushing the decimal point back here. And so here we have 4 significant digits. And one more. Let's change that number to 6.05170. Now how many significant digits do we have? We have 6. These 4 are still significant. The 6 is significant, and now this 0 is sandwiched in between, and so it becomes significant, and here we have 6 sig digs. Okay, we're going to continue with significant digits in the next lesson. We'll see how to do computation with numbers involving significant digits and preserving the correct number of significant digits on our result. But for now, let's see how significant digits are tied to accuracy and precision. The accuracy of a numeric measurement refers to how well the number represents the true value of the item being measured. Here's an example. If someone were 5 feet and 11 inches tall, it would be more accurate to say that they were 2 yards tall, that would be 6 feet, than to say that they were 3 yards tall, that's 9 feet. Now, neither of those two is exactly correct. Most measurements are not exactly correct. It depends on how well the measuring tool can measure, how precisely, in fact, and we'll get into that in a minute. But the 2 yards is still a more accurate statement than 3 yards. It's closer to the true value, therefore it's more accurate. It is the number of significant digits that determines the accuracy of a number. For example, if we say the population of a small town is 1,300 people, since 1,300 has 2 significant digits, we'd say it's accurate to 2 significant digits. If we knew that the population was 1,326, that's more accurate. In fact, it's accurate to 4 significant digits, right down to the exact number of people. A population of 1,326 would be accurate to 4 significant digits. If we had a measurement of 0.300, we would count the significant digits. There's 3 of them there. And so we would say that 0.300 is accurate to 3 significant digits. Now let's contrast that with the precision of a measurement. The precision of a value refers to how specifically a measurement is able to be taken. Again, for example, let's go back to our person that's 5 feet 11 inches tall. If we claimed that they were 4 feet 9.5 inches tall, that would not be very accurate. We'd be more than a foot off. However, we have very good precision. We've measured it to the nearest half of an inch. So we measured it very precisely, but not very accurately. The precision of a number is determined by the location of the last significant digit. For example, 4,500. It's precise to the nearest hundred. Because in the number 4,500, the last significant digit occurs in the hundreds place. We would say that this number is precise to the nearest hundred because this is the location of the last significant digit. These two are not significant. We don't know that it's not 4,508 or 4,499. So this is as precise as we can be. However, we would say that it is accurate to 2 sigdigs. The number 8.590 is precise to the nearest. Where is the last significant digit? The last significant digit, is this 0 significant? Yes, it is. And so this is precise to the nearest thousandth. That's the location of the last significant digit. This tool measured to the nearest thousandth of a unit. And it is accurate to, how many significant digits do we have? 4. So it's accurate to 4 significant digits. The number 225 is precise to the nearest whole number or to the nearest whole unit. Because the last significant digit occurs in the ones place. It is accurate to, that's right, 3 significant digits. Now, here's a way to visualize this. Look at this scale shown on the screen. Do these scales have the same? The scale, as you can see, is broken off on the left. This ruler has been chipped off and broken somehow. Therefore, will the ruler be very accurate? Unfortunately, this ruler will not be very accurate because it's broken. But will the upper and lower scale have the same precision? If you look at the top scale here, the inches are broken into tenths. Therefore, they have a precision of 1/10. The bottom scale has a precision of hundredths. The inches are broken into 100 parts each, and so the bottom scale has a precision of 1/100th of an inch. Both scales are broken, though. So to answer the first question, do they have the same accuracy? Yes. Neither of the scales are very accurate since the scale is broken. Do they have the same precision? No. The bottom scale is more precise. It measures to the 100th, whereas the top scale measures only to the nearest tenth. consider these two scales. Do these two scales have the same accuracy? Well, if you look at the top scale, it's not broken. That ruler is intact. That ruler would be accurate. The bottom ruler is broken. It would not be accurate. So do these two rulers have the same accuracy? No. The top one is very accurate. The bottom one is not. They do not have the same accuracy. Do these scales have the same precision? Again, how accurate the scales are no longer matters. Precision is asking how precisely the tool can measure. Both of these scales measure to the nearest tenth of an inch. So the answer is yes, they do have the same precision, even though they do not have the same accuracy. They'll both measure to the tenth. The top one will do it accurately, and the bottom one will not. That's the end of this lesson on accuracy, precision, and significant digits. In the next lesson, we'll work with real numbers and how to compute preserving the correct number of significant digits.